Today we're going to talk about actor-critic algorithms, building on the discussion of policy gradients from earlier in the week. Class notes, hopefully all of you have turned in homework 1. If you haven't, do keep in mind that there's a maximum of 5 cumulative late days, so that those are all the late days you get. And the only other class note is remember to start forming your final project groups. So that final project proposal will be coming up sooner than you think. Make sure that you have your groups figured out. You can start writing your proposal. You can start even working on your final project. If you want advice on good project topics ahead of the final project proposal deadline, definitely come into office hours, ask the TAs, ask me. We're always happy to discuss project ideas. Okay, today's lecture. So today we're going to talk about improving the policy gradient even further by introducing a second model called a critic. So we'll talk about what a critic is. We'll discuss this policy evaluation problem, which deals with fitting a critic to a policy. And then we'll talk about how it can also be used to improve the policy further. We'll introduce discount factors, which are a very simple but important concept for handling infinite horizon tasks that we haven't discussed yet. And we're going to put this all together into the actor-critic algorithm, a batch mode actor-critic algorithm, and also an online actor-critic algorithm. So the goals for today will be to understand how policy evaluation fits into policy gradients, understand how actor-critic algorithms work, and that's it. And then look at some examples of papers that have done deep reinforcement learning with actor-critic algorithms towards the end. All right, so to recap from Wednesday, policy gradients. So this is the kind of simple version of the algorithm that we covered on Wednesday. It's the reinforced algorithm, also referred to as the policy gradient algorithm, the likelihood ratio policy gradient algorithm, and so on. That all refers to the same thing, which is this. And this algorithm consists of just 3 steps. In the first step, you sample some trajectories by running your policy. In the second step, you use those samples to estimate the gradient of the expected total reward by using this grad log pi trick. And then in the third step, you apply this gradient to modify your parameters via gradient ascent. So just like all of the reinforcement learning algorithms we'll cover, it has 3 parts: sample generation, fitting a model or estimating the return, which is very, very simple. It just means summing together the rewards, and then improving the policy. So estimating the return just means you estimate this reward to go, Q hat, by summing together the rewards, typically from the current time step until the end. And improving the policy means that you apply the gradient, where the gradient is estimated using samples. So in today's lecture, we're usually going to write the policy gradient like this, using some kind of symbol for the reward to go, because what we'll do today is we'll talk about all the different ways that this Q hat thingy can be estimated. So we saw just one way on Wednesday, which is by summing together the rewards, by doing this thing. Today we'll see other ways to estimate this Q hat. The meaning of Q hat IT here is the total reward from now until the end of the episode, or as we'll see in infinite horizon problems, the total reward from now until forever. So this is the reward to go, and this is the quantity that we'll be concerned with. So let's talk a little bit about this reward to go. So this Q hat, it's an estimate of the expected reward. This T prime should actually be a T. Sorry, there was a typo on the slide. The Q hat is the estimate of the expected reward if you take an action A in a state S, right? So the way that we're computing this expected reward is by summing together the rewards that we actually got along a single trajectory. Can we get a better estimate? So if we look at this visually, this is our trajectory. This is the time step t at which we're sitting, indicated by this green circle. And what we're estimating at this time step t is Q hat of I comma t. So it's the ith trajectory, the tth time step along that trajectory. How do we estimate the reward to go? Well, we can take all the remaining rewards in the remaining part of this trajectory, and we can sum them together. But we have a stochastic policy and stochastic dynamics in the most general case. So this trajectory that we got here, the future from this green spot, is one of many possible outcomes. So if you were to revisit this exact same state again and take the same exact actions, you might get a completely different outcome. You might not get this thing. So when you estimate Q hat with a sum of the rewards that you actually got, what you're really doing is you're approximating an expectation over all possible stochastic events that could have happened over here with one sample. Now, estimating expectations with samples is an unbiased estimator. Even when you use just a single sample, it's still unbiased, which means that in expectation you get the right answer. And of course, we already knew this because we knew that the policy gradient is indeed an unbiased estimate of the gradient. So there is no bias introduced by doing this, but because it's a single sample estimator, it might have high variance. So in reality, there are many possible outcomes, and the ideal estimator for this thing would actually take into account the fact that there are many possible things that could happen, and it would provide a better estimate of the expected reward in the future. So what you really want to plug into the policy gradient is the expectation of the sum of rewards from time step t until the end. And the expectation is taken under the policy and under the transition probabilities. So if you knew Q of ST80, this is the Q function as we discussed last week, which is defined as the total expected reward after you take action AT in state ST, this would be a better estimate that you could use in place of the sum of rewards for Q hat. So if you had access to the true correct Q function and you plugged it in here into the policy gradient, this would be a lower variance policy gradient because you've gone from estimating Q hat with a single sample to using the true expectation. And in reality, of course, we want actions that are better than average to increase in probability and actions that are worse than average to decrease in probability. So what we might also choose to do is instead of plugging in the true Q, you can plug in the true Q minus the true V, which is a measure of how much better that action is than the typical action from the policy, since the value function is defined as the expectation of the Q function under the policy. And that's what we refer to as the advantage. All right, let's dig into this a little bit more. This is a very quick high-level overview, but we'll dig into this in more detail. So if we had the true reward to go, the true Q function, which gives us this expectation over all possible future random events from time step t, we can plug it into our policy gradient to get a lower variance estimate of the policy gradient. We can also subtract a baseline from it, and we learned about baselines on Wednesday. We learned they're actually quite important to reduce variance. A good baseline that we learned about on Wednesday is to use the average reward. You can actually have your baselines depend also on state, and in fact in homework 2, there's actually a problem where you'll prove that it's okay to have baselines depend on state. So then you say, well, average what if you have a Q? You're not summing rewards anymore, you are taking the full expectation, so maybe you average over all possible actions. And that's what the value function does. So maybe you have many possible actions, you average together the Q values, which is exactly the definition of the value function, so you can plug that in, and that's kind of the equivalent of a state-dependent average reward. You can't have that if you just have a single sample estimate, because obviously the average reward from that single state on a single trajectory is the total reward you got, so there wouldn't be anything happening here. But if you have the true value function, then you can actually do this, and you get a lower variance, and this is exactly the definition of the advantage. Okay, so let's, to make sure we're all on the same page, let's just recap the definitions of state and state action value functions. If you hear someone say state action value function, that means exactly the same thing as Q function. So the state action value function, or Q function, is defined as the sum of expected rewards from the current time step until the end, given that you start off in state ST and take action AT. And we will often write the Q function with a superscript pi to make it clear that this is the Q function for a particular policy, because those expectations are taken under the transition dynamics, the transition probabilities, and a policy. So if you see me write Q superscript pi, that means the expectation will be taken under pi. V pi is just the expectation of the Q function with respect to the action. So the Q function tells you what's the total reward that you get if you start in state ST and take action AT, and then follow the policy pi. The value function tells you if you start in state ST and then follow the policy pi. Right? So one depends on the action, the other doesn't. The advantage function is just defined as the difference between the Q function and the value function. And the reason we call it the advantage function is because it describes how much more advantageous is the action AT over the average action from the policy. So since V pi of ST tells us the value under the policy, the difference between the two tells you how much better is the action AT on average than the action the policy would have given you. And of course, if you modify your policy so that actions with large advantage become more likely and actions with low advantage become less likely, then you will get a better policy. So that's what this expression for the policy gradient from the previous slide is doing. Now, of course, in reality, we don't have access to the true Q pi or the true V pi. We have to approximate them in various ways. The better that estimate, the more accurately we approximate the Q function and the value function, and therefore the advantage function, the better our policy gradient will be. So when we use the policy gradient that we learned about on Wednesday, this policy gradient is estimating the Q function by summing together the rewards along the single trajectory that you saw, which is an unbiased estimate for the Q value, but it is a high variance estimate because it's using just a single sample. So this is correct. It's a correct expression in the sense that if you evaluate this enough times with enough samples, you will on average get the right answer, but you will have higher variance because you're using a single sample to estimate the Q value. Okay, so what we can imagine now is we can imagine modifying our policy gradient algorithm so that we still collect samples, we still use the policy gradient to improve the policy, but now in the green box, we can actually do some additional modeling. We can fit some kind of function approximator to give us a better estimate of Q pi and V pi and therefore A pi. A better estimate than what we would get by summing together the rewards along a single sample. Does anyone have any questions about this? Yes?
Can you explain why the better the estimate of advantage, the lower the variance?
Right, so the question is, well, why is it that the better the estimate of the advantage, the lower the variance? If you, let's say that you average together two samples, like somehow you could just teleport back to that state and try again. So you could teleport back to SIT and then take action AIT again and then run your policy. Now you would get a second sample that you could use to get a better estimate of this total reward to go. So if you estimate a quantity, an expectation of some function with one sample versus with two samples, using more samples gives you lower variance. Now the trouble is that we can't just teleport to the same state twice and try again in general, especially if we're learning in the real world. So then we need to do something a little more clever than just hoping to generate multiple samples from the same state. And that's what the rest of the lecture will cover. Okay, so value function fitting. What we're going to do is we're going to try to fit function approximators, actually neural networks, to something like this. So something that's either going to give us Q pi or V pi or A pi. And of course, the question that we need to ask now is, well, there's three objects that I introduced, Q pi, V pi, and A pi. So what are you going to fit? And what are you going to fit it to? Like, what are going to be the targets? So you can fit Q pi, V pi, or A pi directly. Actually, there are actor-critic algorithms that do different things here. So there are some that fit Q, some that fit V. I don't know of any that fit A, but they probably exist. So all of those are actually legitimate choices, but there are a few considerations that we can consider to help us choose which one we should be fitting. So first, let's look at the Q function a little bit more closely. The Q function, as I wrote it out before, is this sum of expected values over all the time steps from now until the end. But remember that the Q function is a function of ST and AT. So ST and AT are not random here. You're not taking an expectation over ST and AT, only over ST plus 1, AT plus 1, ST plus 2, etc. But the first state and the first action are given, which means that you can equivalently write it like this. The Q function is the reward at ST-AT, which is not a random variable. This is a deterministic thing, plus all this future stuff, which does depend on random variables. So this future stuff is stochastic, but this thing, since you know ST and AT, that's just a number. And this future stuff, this is the expectation of the value function at state ST plus 1. So you can equivalently write it like this. The current reward plus the expectation of the next value, and the expectation is taken under the transition probabilities. Now, so far, we haven't made any approximations. This is just an exact equality. And now, what we can do is we can introduce just a little bit of an approximation. We can say, we're going to use the full value function, but we're not going to use the full integral over all possible next states. We'll actually approximate it with the single next state that we got on our transition. So now this is an approximation. It's still unbiased because if the value function is correct, because st plus 1 was indeed sampled from the transition probabilities. So we lost a little bit of accuracy there. We're introducing a little bit of variance. But it turns out to be very convenient to make this approximation. Because now, after we've made this approximation, we can write out the advantage function. Remember, the advantage function is the q function minus the value function. And if we substitute in this equation for the q function, then the advantage is just the current reward plus the next value minus the current value. So now everything is expressed in terms of v pi, and v pi is only a function of the state rather than a function of the state and action. So that's very convenient because that says that if we're going to accept the small approximation over here, which is that we're going to sample a single value for the next state rather than the full integral, then everything can be written out in terms of a function of only the state, which is perhaps easier for us to fit than a function that depends on both the state and the action. So for this reason, actually, most actor-critic algorithms fit the value function. However, this is not the only choice. There are also actor-critic algorithms that fit the q function directly, and there are some advantages to that we'll discuss when we talk about off-policy algorithms next time. But for today, we'll talk about algorithms that fit the value function. And that's actually what you're going to also do in homework 2. Question?
So we're using a single sample estimate here for the v pi, but we had a single sample estimate before. Like, how
right. So the question is, it seems like we're using a single sample estimate here. Isn't this kind of terrible? The important distinction between this and the sum of rewards that we saw in the policy gradient is that this is a single sample estimate for st plus 1. But v pi itself is still trying to estimate the full expectation of everything that happens in the future. So if we were to go back to the picture I had before, so I had this picture where we had a trajectory and you had many possible things coming off of it, right? So these are the things that you're integrating. Now, when we use a single sample estimate for st plus 1, what we're doing is we have a trajectory, then we do one step with a single sample, but then after that, we still have all the different possibilities. So assuming that this bit is much larger than 1, then you still get a lot of variance reduction, even though you used a single estimate for this one step. Okay. So let's just fit v pi. Let's work with that and see where that gets us. So we're going to use a neural network or some other kind of function approximator that's going to estimate this v pi. And we're going to call it v hat pi to emphasize that it's an estimate. It's not the true value function. It's going to be a function approximator will attempt to estimate the value function. So we're going to fit this v pi, this v hat pi of s, and it will have some parameters phi. In general, this function approximator might be completely unrelated to the policy. So maybe the policy has parameters theta, the value function has parameters phi. We'll talk about later on how we can actually put them together too. Okay, so fitting v pi is referred to as policy evaluation, because it's trying to evaluate the value function for a policy. Fitting v pi itself is not actually modifying the policy. It's just trying to answer the question, how good is this policy in any given state? So that's going to be the green box. The green box doesn't change the policy. The green box just estimates something about the policy that can be used later on in the blue box to improve it. So policy evaluation refers to estimating the value function or the q function for a given policy without changing that policy. Now, remember that the reinforcement learning objective is the sum of expected rewards for all the time steps, which means that if you can fit the value function, the reinforcement learning objective is just the expectation of the value function under the initial state distribution. So learning a value function is going to be actually quite useful to us for improving our policy, and it'll give us the value of the reinforcement learning objective. So we can actually find out how good our policy is overall just by evaluating the value function in the initial state distribution. So how do we perform policy evaluation? Well, we need to construct estimates for this value function and fit to those estimates. So one of the things we can do is we can use Monte Carlo policy evaluation. Monte Carlo policy evaluation is actually what the policy gradient from Wednesday does. It just refers to taking samples and summing together their rewards. So Monte Carlo policy evaluation says that the value function for a particular state is approximately equal to the total rewards that you get when you start in that state and then run your policy. So that basically amounts to saying, well, let's look at all the states that we visited. Maybe we look at this state along our trajectory, and we sum together the remaining time steps, and that gets us an estimate of the value of the policy in that state. We can get a better estimate if we can do this Monte Carlo policy evaluation with multiple samples. So if we could actually teleport back to this state and try multiple times, then we could generate multiple samples from I equals 1 to n from a single state, average them together, and we get a better estimate of the value. Of course, in general, we can't do this because this requires us to have some kind of simulator that we can reset back to the same exact state that we were in before and try again. Sometimes you can do this, but in general, we would assume that we cannot do this. Although if you could, this is actually a good way to get a more accurate value for the value function. Fortunately, if you're using function approximators to fit vpi, you actually can still get a lot of variance reduction without having to teleport back to a state that you were in before. So we're going to be fitting this v hat pi, and we're going to use the simple Monte Carlo policy evaluation where we just sum together the rewards just along the tail piece of this trajectory. And the reason that we'll still get a variance reduction from doing this is that this function approximator will be fitted not just in a single state, but in many states, each of which will be labeled with these kinds of value estimates. So we're going to sum together the remaining rewards along that trajectory, but not just that one trajectory, we'll have some other trajectory. And maybe that other trajectory visited a state that is not exactly the same, but it's similar, maybe it's close by, and that will have a different target value from summing together its remaining states. So even though these states are not the same, the function approximator will realize that they're close together. Maybe they're close together in terms of Euclidean distance, and you will get an amortization effect, which means that it'll, to some degree, average out the values at these two states simply because these two states are similar. So this is because you're doing function approximation. So the same function is going to try to fit both of these samples, and if both of these samples have very different values associated with them because of the variance in this return, the function approximator will actually average them out. For example, if this one is better and this one is worse, it'll probably say that, well, this is here you got some noise, you're worse than you should be. Here you got some noise and you're better than what you should be. So it'll make the better one look a little worse and the worse one look a little bit better. Not as good as if you were to actually take multiple samples from the same exact state, but still achieves variance reduction. So it's still pretty good. And of course, you can imagine that if you generate infinite samples, eventually, even though you might not see the same exact state twice, you will see so many states that are similar that it will eventually, given enough samples, be as good as this thing as the number of samples goes to infinity. Question?
How do we actually evaluate if these kind of approaches are actually resulting in a reduction of variance in practice?
Right, so the question is, well, how do you evaluate if this approach results in a reduction in variance? You can measure the variance of the policy gradient. You can actually, generate n samples again, and again, separately compute the gradient for each group of n, and measure their variance.
You should be on the same state as you, resetting back to something.
Well, so to be clear, variance of the policy gradient refers to the variance of the entire gradient, not to the variance in a particular state. So that's what you really care about, because that's the gradient you'll actually be applying to your parameters. So in that sense, it's enough to generate multiple samples straight from the initial state distribution. Okay, so not as good as this, but still pretty good. So let's just make this learning problem concrete. What are we fitting and what are we fitting it to? We're going to fit this neural network that takes in a state and outputs an estimate v hat pi of the value. And we'll do it with supervised regression by constructing a training set where the inputs consist of the states that we've seen, and the outputs are going to be the total rewards, these rewards to go from our policy from the trajectory that we actually got. So we'll generate a bunch of trajectories. For each trajectory, for every time step, we'll drop that state in as an input into our training set, and we'll drop the sum of the remaining rewards as the output into our training set. So we're going to get this training set of states and total rewards. And for notational shorthand, I'm going to refer to these outputs as YIT. So state SIT, the state from the ith trajectory at time step t, is going to have the label YIT, which in this case is going to be the total remaining reward in that trajectory. And then we just do supervised regression, right? So we're just going to minimize this loss, the square of the difference between the output of our function approximator and our target value at everything in our data set. And this is an optimization with respect to phi, which are the parameters, the weights in this v hat pi neural network. So that'll allow us to fit our value function. Okay, so that's actually a workable way to do this, and you'll actually be doing something very similar to this in homework too. But maybe we can do a little bit better. So this is nice. It will reduce variance, but we can do a little bit better. So what's the ideal target? What do we wish we had as our labels YIT in our data set? What we really wish we had is the actual expectation, the sum from t prime equals t to capital T of the expected value of the reward. Can we get something that is closer to this expected value than what we had over here from just summing together the rewards? So this is the Monte Carlo target. This is what we had before. But this full expectation, we know from before that it's approximately equal to the reward at time step t plus the expected reward that's to go, which we saw before that we can approximate with the next value function. Now there's a little detail here because, of course, until we've actually fitted v pi, we don't have a good estimate for this thing. But what we can do is we can say, well, maybe I would rather have a lower variance target, even if I have a slightly incorrect value function, than an unbiased target with higher variance, which is what I would have over here. So perhaps what I could do is I could grab the value function from the previous iteration of my algorithm, which is not the same as the value function for the current iteration, because the policy has changed between then and now. So I'm going to grab my old value function, which is a little bit wrong, but it's actually trying to estimate that full expectation, so it'll have lower variance. So what I can do is I can substitute it in v hat pi, but this is my previous v hat pi. So this v hat pi is incorrect. It is the v hat pi for the wrong pi, essentially, my previous pi. But it's going to have lower variance because it's trying to estimate that full integral. So I'm going to trade off a big decrease in variance for an increase in bias. And in practice, this trade is often worth it because your policy might change by only a small amount between iterations. So the value function is still a good estimate, and it gives you very dramatic reduction in variance. So you can just directly use the previous value function that you fit it. So now your training data will consist of all the states that you sampled from your policy, and the label will be the reward at that time step plus your previous value function evaluated at the next state along that trajectory. So this will be lower variance labels with some bias. And again, we're going to, for shorthand, refer to this as YIT. Yes?
It seems that we're using the same formula for the YIT that we did for like the approximation for Q. It was also a reward plus v pi. Why is that
Yes?
okay to do?
Why is that okay to do? Well, so you're not actually going to plug this quantity into your advantage estimate. What you're going to do is you're going to refit your function approximator, and then you'll fit your function approximator into your advantage estimate. So this is not the advantage estimate. This is just the target for your value function. You'll fit your neural network to this. And when you fit your neural network, you will get this amortization effect that we had back here. So your neural network will realize that, oh, you have a state over here with one value, a state over here that's very similar with a different value, and it will average them out and do all that stuff. And then that's what you'll use in your advantage estimate. So to put another way, these terms won't actually cancel out because you're not going to be plugging this directly into A and then subtracting the v pi. Yes?
What we are trying to do to reduce this variance does not affect the accuracy, or we're only talking about how it affects the variance, but what about the accuracy?
Right, so the question was, we're only talking about how it affects the variance, what about the accuracy? So put another way, there is variance and then there is bias, right? So you want the correct answer and expectation, and you want to get an answer that has relatively little difference between different sample batches that you draw. So the difference between sample batches, that's variance, the correctness and expectation, that's unbiased. So this will give you an incorrect answer in the sense that it will give you a biased answer because this value that you're putting in there is not the value function for your current policy. So this will be incorrect. But the usual story with variance and bias, it's like a signal to noise ratio thing, right? If I have if I have some ground truth signal like this, and I give you a very high variance read on this signal, I give you something like this, right? Maybe it's very hard to recover the signal from this very high variance reading, from this very noisy reading. Maybe you would rather that I give you a slightly biased but relatively noiseless version of that signal. Because in the end, what you care about is what you're going to estimate from samples. So if you have a small number of samples, even though you're unbiased in expectation, from any given set of samples, you might be pretty far off. So maybe you'd rather I give you this slightly incorrect but low noise signal instead. And that's what we're doing here. We're basically giving you a slightly incorrect signal, but with much less noise, because this v hat pi is going to be estimating that whole integral. Yes?
After retraining this, finding estimate of the value function, we should go back to our policy and retrain our neural net for the policy, right?
Yeah. So the policy improvement I'll get to later. For now, I'm just talking about policy evaluation.
But we can use this value to also just get around that, finding the theta values, just coming up with the actual policy based on these values.
Yes. So to answer your question, you can use the fitted value function to recover a policy. We'll actually talk about that next week. And today we'll just talk about how to plug it into the policy gradient. Yeah. OK, so once you compute these R plus next V, you plug them into the same regression objective just like before, minimize squared error, and you get a new estimate of the value function. And this is sometimes referred to as a bootstrapped estimate. There's a fairly nuanced technical reason why this is referred to as bootstrapped. It's actually similar to the bootstrap in statistics, but I'm not going to go into that too much. The point is that you're just using your previous value function to cut off the rest of that integral. Yes?
I think the loss function here is just like the advantage function in projection.
OK, so the question was, the loss function here looks a little bit like the advantage function if you take this thing and plug it in here. There's a little bit of notational nuance that unfortunately this slide doesn't get across very well. When you optimize this objective, you're only optimizing through this thing, so you're treating the y's as constant. So even though you used phi up here to derive this target, you're not actually pushing gradients through this phi. You're just computing these numbers, storing them in a buffer, and then treating them as though they're constant labels. So the optimization is only with respect to this first term. And this is actually important. This will come back when we talk about Bellman error minimization for Q-learning later on in the course. So for now, this is just a constant, but we'll talk about that more later. Yes?
When you're optimizing this, do you just take like one gradient step, then re-get your new training data from that new updated value function, and then keep doing it like that?
Right. So the question, this is kind of jumping ahead a little bit, but the question was, well, OK, you could get an even better target if you were to take this objective, optimize it for a little bit, take the resulting new v hat pi, plug it in here, and now maybe this should be a better target because now the value function looks more like the value function for the new policy, and you could actually alternate these steps. The answer is yes, you could. It has some advantages and some disadvantages. The advantages are fairly obvious, which is that you get better targets. The disadvantage is that it's a lot harder to make the resulting procedure actually converge, because essentially what can happen under function approximation is that if this v hat pi makes a mistake, it's a function approximation, so it'll make mistakes. And if it erroneously says that some state is better than it really is, that state will get a larger target value, and it'll become even better. So it's a good idea. In practice, stabilizing that procedure can be a little bit hard, but it could work. For now, let's just say we do this once per outer loop. So once per policy. OK. So this was all a discussion about how to do policy evaluation, the green box in that diagram. Now, policy evaluation, so far I went through it a kind of, in a mathematical sense, which is somewhat abstract, but it actually has a very intuitive interpretation in many cases. For example, in the first lecture of the course, I talked about this thing called TD Gammon. TD Gammon was, in some sense, one of the first deep neural network game playing systems that could beat expert human players, although it was not called deep reinforcement learning at the time. But it was basically reinforcement learning combined with neural network function approximation for playing backgammon. And there, policy evaluation had a very natural interpretation. Policy evaluation meant you fit a value function to the current state of the board. The reward is to win the game. So the value function actually tells you, given the current board state, how likely are you to win the game. So that's a very kind of natural thing to try to predict. It actually makes a lot of sense. You could actually look at the numbers and you can say, oh, the value function is telling me whether this is a good board state or a bad board state. It's telling me how likely am I to win. AlphaGo, same thing. The value function is the value function for the game outcome reward. The game outcome is just did you win or did you lose. So the value function tells you the expected outcome, how likely you are to win or lose, given the current state of the board. So policy evaluation actually makes a lot of sense. Yes, question back there.
Does policy evaluation lead to Q values in the infinite limit as your distribution over actions approaches optimal?
So the question was about the relationship between policy evaluation and the optimal Q function. The important thing about policy evaluation is that it's not trying to change your policy. It's just trying to answer the question, in this case, how likely are you to win given a policy? So you say, here's my strategy, here's my policy. Tell me, will this policy win given that the Go board is arranged like this? There is a separate thing you can do, which is then use this quantity to give you a better policy, but that's separate from policy evaluation. Yes?
Is the reward win or lose, or is it the number of points you get ahead, and will the algorithm maybe take some chances and risks to have even more?
Yeah, so for these particular examples, I don't know, I don't remember, but we could go and read the paper and figure it out. I think that backgammon actually, the TD Gammon thing actually did have a win or lose reward, but I'm not certain about that. But certainly you could use more complex reward functions and you could set them up so that there's a notion of risk and so on, yeah. Okay, so now that we've talked about policy evaluation, let's actually put the pieces back together. We've got our policy gradient algorithm, we've got our policy evaluation. Let's put them together to get a complete actor-critic algorithm that can actually improve the policy using these estimated value functions. So what I have written out here is a batch mode actor-critic algorithm, which essentially extends on the reinforce algorithm that I showed you at the beginning of the lecture by introducing a value function critic. So the way this algorithm works is that it samples trajectories by running your policy just like before. Now it's going to have a new step where it's going to fit v hat pi to the sampled rewards. Then it's going to estimate an advantage for every single time step along every single trajectory. And it's going to estimate that advantage by taking the reward that you actually got, the value function at the next state minus the value function at the current state. And then it will plug those advantages into the policy gradient expression. So before we had grad log pi times reward, total rewards. Now we have grad log pi times advantage. And then just like before, you do gradient ascent on the policy parameters. So now the green box is a bit more complex. The green box involves actually doing this policy evaluation and fitting v hat. And the blue box is exactly the same, just using v hat inside the advantage estimator instead of simply summing the rewards together. And of course, there are a few choices for how you fit v hat pi. Here you could, for example, do the Monte Carlo thing, so sum up the rewards along the trajectory, which, even though it's still using a single sample estimate, will still give you benefit. It will still give you variance reduction because the function approximator will realize that very different rewards at very similar states should actually be averaged out. So that's from the benefit of function approximation. You could also do the bootstrapped estimate where you actually add the next value. This will give you even lower variance at the cost of introducing bias It'll introduce bias because you're not really using the right value function over here. You're using a stale, slightly older value function. All right, so this is a batch mode actor-critic algorithm. It looks similar in structure to the reinforce algorithm in that you sample these trajectories, except that you have these additional steps, the steps 2 and 3, to evaluate the value function. But actually, now that we've derived the actor-critic algorithm, we can actually change it a little bit, and we can actually get a fully online algorithm, an algorithm that can improve the policy every single time step without having to collect multiple trajectories. Before we get into that, we need to talk a little bit about how to set up reinforcement learning with policy gradients for problems with an infinite horizon. So far, we've talked about these problems that have capital T time steps, right? You sum from something to capital T, that they have fixed horizons. Sometimes fixed horizons are very natural, but sometimes you want to deal with episode lengths that go to infinity. So a fixed horizon is fine, for example, if you have a robot performing some episodic task. Like this robot wants to learn to stack the Lego block. It's the Lego block stacking task takes exactly, let's say, 5 seconds, and that's an episode. But some tasks are more continuous or cyclical or periodic. Like maybe the running robot doesn't need to run for exactly 10 seconds. The running robot needs to be able to run forever. So the goal there is to optimize a policy that can run for as long as possible and ideally forever. And we saw when we talked about the objective for reinforcement learning that you can write down a reinforcement learning objective for infinite horizon problems by reasoning about stationary distributions. But now, we talked about this machinery for estimating value functions, and we had this funny thing where we take the reward and add the next value. Now imagine that here, t goes to infinity, capital T. If capital T goes to infinity, now every time you update your value function, you take some number that you had before, add something to it. Let's say your rewards are always positive. So you take some number before, you add a positive number, and then you repeat. So you keep adding numbers to it. You keep making your values bigger and bigger and bigger and bigger, and they'll just keep getting bigger until they go to infinity, and everything will be terrible. So here, you know, too much of a good thing is actually not good. Too much reward goes to infinity, and you can't learn anything. So we need to somehow address this problem. It actually turns out to be very easy to address this problem. We do it using something called a discount factor. So a discount factor basically says that receiving rewards sooner is better than receiving the rewards later. So it's a simple trick. It's better to get rewards sooner than later. So if you were to tell me that you'll give me $1 million, I'll be pretty happy about that because $1 million, you know, that seems like a good thing. If you then tell me that you'll give me $1 million in 100 years, I'll be a bit less happy. I mean, maybe I'll still be happy with it because, you know, maybe my descendants can use that money. And if you tell me they will give me $1 million in a million years, I'm just going to think that you're joking with me, right? That doesn't really make much of a difference in my life. Why is it that I would rather have the $1 million now than 100 years from now? Does anyone have any hypotheses? Well, serious question. You guys can try to answer it. Yeah. Inflation, yeah. So maybe the reward will be worth less later. Is there any other reason? Yeah.
You could like invest the money if you get it now, and then you could like.
I could invest the money. I get more money later. You guys are very financially oriented. I think there's actually there's an answer back there.
You might not be alive.
Yeah.
What's that?
You could die.
I could die. Yeah. I mean, I would be maybe pretty happy if I live 100 years longer, but that seems unlikely. So I might die. And that's a good answer. The thing is, the future is uncertain, and all sorts of stuff can happen, and maybe you prefer the rewards sooner rather than later because you might die. So the way that we can formalize this idea of getting rewards sooner rather than later is by putting a little multiplier on the value function, this little multiplier gamma. And this multiplier gamma is a number between 0 and 1. Usually we pick a number that's pretty close to 1, so 0.99 works well. And mathematically, what that will do is it'll cause this thing to converge, because if you expand this out, you essentially get this geometric sum. So 0.99 raised to the power of however many time steps it is in the future eventually adds up to a finite quantity. So we don't have this problem with everything going to infinity. But then, of course, you might ask, well, is this just a hack, or is this actually doing something that's meaningful in a modeling sense? So the answer before was that, well, maybe the reason I prefer rewards sooner rather than later is because I might die. And that's actually what gamma is doing. It's modeling the fact that you think you might die, like literally. And I'm going to show you this right now. So here's how we're going to show that gamma models your fear of mortality. I'm going to draw an MDP, a very simple MDP, with 4 states. It can be any number of states, but I just drew 4 because that's a small number that I can put on a slide. And these states, you can transition from one to the other. And of course, your transitions are governed by transition probabilities, P of st plus 1 given st. And this value function, what you should really do is you should compute its expectation under the transition probabilities. So there's a probability P of s prime given s comma a. And we just happen to have sampled it here, but what we should have really done is taken the expectation. When you put a gamma in front, what you're really doing is you're actually modeling a new MDP where these transition probabilities are multiplied by gamma. Now, of course, they still need to sum to 1. So when you multiply all of your transition probabilities by gamma, you still have this little 1 minus gamma piece that needs to go somewhere. And where does it go? Well, it goes to death, right? So there's a probability of 1 minus gamma that you will die every single time step, which means that all of your other transitions have to get multiplied by gamma so that the total still adds up to 1. So when you put in this multiplier of gamma, what you're really saying is that now I live in a slightly different MDP where with probability 1 minus gamma, I will die, and when I die, I receive no more rewards. So it's sort of a very particular kind of religious worldview. You die, you receive no more rewards. The rewards only happen while you're alive, and your probability of dying is 1 minus gamma. So in fact, it's still an MDP. It's just a different MDP, and it's not a hack. It actually makes sense. OK, so that's kind of the theory. But now, how do we actually use the discount factor in a policy gradient? Well, it turns out that there are actually 2 ways we can instantiate this theory in a policy gradient algorithm, and they lead to slightly different outcomes. So let's just deal with regular Monte Carlo policy gradients for now, none of this value function business. So one thing you can do is you can take your grad log pi, and when you estimate your reward to go, you discount the reward to go by gamma to the power of t prime minus t. So the first reward gets a multiplier of gamma to the 0, which is 1. The second reward gets a multiplier of gamma. The third one gets a multiplier of gamma squared, and so on and so on and so on, which makes perfect sense. It says that rewards received sooner are worth more than rewards received later. A second option is to rederive this thing starting from the original policy gradient, where you have the sum of the grad log pi's times the sum of rewards. And what we can do is we can distribute the sum, and we can use the causality trick, and so on. And if we do that, well, and of course we can do it with a critic also. If we do that, we actually get a different answer. So these 2 things are not going to be the same. So let me just walk through that a little bit. If you distribute the sum and you use the causality thing, you get the sum from little t to capital T. But your gammas now, turns out they're going to be t prime minus 1 rather than t prime minus t. And you can rewrite it a little differently in a way that will make it a little clearer what's going on. You can take this t prime minus 1, and you can multiply it by, or divide it by gamma to the t, and that'll give you a gamma to the t minus 1 factor out here, and a gamma to the t prime minus t factor out here. This is just equal. I just moved one of the gammas over. And when I do that, now it becomes a little clearer how exactly these 2 things are different, because now this bit and this bit is exactly the same. The only difference is that over here, there's a gamma to the t minus 1 in front of the grad log pi, whereas over here, that factor is absent. So these are 2 different discounted policy gradient estimators that I can write down. Which one is better? Does anyone have any thoughts about which one they prefer, option 1 or option 2? Does anyone have any thoughts about how option 1 and option 2 might change the behavior of the agent?
Option 2 is short-term.
Say that again?
I think option 2 is short-term policy.
Right, so the answer was, it seems like option 2 is some kind of like short-term policy. Like it's not really reasoning about long-term consequences as much. And in particular, it's not going to make as much of an effort to modify the policy at later time steps. It's going to really prioritize what happens close to the initial state. So later steps essentially matter less for this option 2. Now, which one is good and which one is bad? Well, let's dig into this a little bit more. Which version is the right one? So this model, where the discount factor essentially models your probability of death, it actually exactly corresponds to this option 2. Because if you think that you have a probability of dying every single time step, and you're going to modify your policy, you should modify your policy so that you act more optimally in the earlier time steps, because you might never even get to the later time steps, so what's the point of over-optimizing them? So in some sense, this option 2 is actually the right answer in light of this kind of death model of the discount factor. So it says later steps basically don't matter if you're dead, so you should just make sure that you optimize for the right thing early on. But option 1 is what we actually usually use in practice. Why is it that we usually use option 1? Well, the reason that we might want to do all this discount factor business is because we'd like to solve problems that are continuous or cyclical, something where something like this running guy, where the goal really is to keep running. So in a sense, even though this death model is very intuitive and appealing and it kind of explains why you might want to use a discount, it doesn't necessarily actually explain the way in which, the reasons why we wanted to go to discount factors in the first place. The reason we wanted to go to discount factors in the first place was to handle these continuous and cyclical tasks. And this death model actually will do worse in that case because it'll over-optimize how well the guy does at the beginning when he has to start running and not really care so much about the middle part of the run where he has to remain cyclical. So option 1 is not actually the correct gradient for a discounted return model, but you can actually interpret option 1, which is the one that everyone actually uses, as something a little different. Option 1 can actually be interpreted as an approximation to the average reward, to the gradient of the average reward, without a discount. And this is discussed in more detail in this paper by Philip Thomas. I'm not going to go into the math in detail, but what I would like to do is say a few words about the intuition behind this idea. The intuition behind this idea is that what you really want is you want to get rid of the discount. You want to basically take the limit as gamma goes to 1. The limit as gamma goes to 1 will give you the gradient of the total average reward. You can put like a 1 over capital T in front so that things stay finite. But you don't actually want to do that because rewards further in the future are highly uncertain. Basically, the more you go into the future, the more variance that adds, until eventually the whole thing becomes completely unstable because the variance grows without bound. So gamma is actually serving as a little bit of a variance reduction thing. It's acting to cut off the signal from those very distant future rewards that are so far in the future that their value might as well be random. So they're only going to mess you up. They're not going to really help you get the right answer. So you might as well zero them out after it's too far in the future. Pay more attention to the nearer rewards because those are more likely to actually be accurate estimates, and use that as a biased but lower variance estimate of the average reward. And the average reward is what you really want in many cases when you're dealing with problems like this. So this is a little bit subtle, and the math behind this is covered in more detail in this paper by Philip Thomas, but I just wanted to mention this just so that all of you can keep in mind that discounts can serve slightly different purposes, and usually the purpose we're concerned with actually is more like this one. So while this model makes a lot of sense and it really explains what discounts are doing in the classical sense, in practice, more often we're over here, and it's really more of a variance reduction technique. Yes?
So as far as I understand, discounts also have another use, which is that when your reward is often delayed. So for instance, when you're playing chess, for instance, if it goes on for 60 moves, you don't get any reward until you actually finish the game. So as far as I understand, discount also applies if you want to then track back and then reward based on what you got it.
Right. So the question is about discount factors and delayed rewards. I think actually what you're thinking of is a little different. There is another concept which I'll briefly introduce towards the end of the lecture called eligibility traces, which does deal with credit for delayed rewards and looks a lot like a discount, but actually works a little differently. So hold that thought. I'll talk about that a bit later. Question back there?
Is anybody using non-hyperparameter tuned discount rates? So learned discount rates or?
So usually in reinforcement learning, the discount factor is actually taken to be a property of the problem. Why is that the case? Well, it's actually somewhat of a historical artifact because originally the model for discount factors that was sort of dominant in the reinforcement learning research community was actually this model, which is very logical and makes a lot of sense, and it says that the discount factor should be a property of the problem. So in the same way that your transition probabilities are part of how nature works, your probability of dying is part of how nature works. You don't get to choose it. When you look at discount factors as a variance reduction technique, which is what's going on up here, then it makes sense to treat it as a hyperparameter, but it's kind of a weird hyperparameter because it actually changes your estimate of the returns. So you have to be a little careful with how you set it up. All right. So now we can put the discount factor into the actor-critic algorithm, and having done that, we can actually derive a variant of the actor-critic algorithm that is online, in the sense that it doesn't have to sample a bunch of trajectories like this batch mode algorithm, but it can actually update the policy every single time it takes a step, even for tasks that don't have a natural episodic decomposition, tasks where you're just acting in the world continuously. So the online actor-critic algorithm looks very similar to the batch mode actor-critic algorithm, but the steps are just a little bit different. So step 1 is actually just to take an action. So this is one step. You sample an action from your policy, you take that action, and you observe a transition, S, A, S prime, R. Just one transition. Step 2, you're going to update your v hat pi. You would update it probably for a very small number of gradient steps, maybe just one gradient step, using the target given by R plus the next v. Now, you have to use a value function if you want to do this online, of course, because if you were to actually sum together all the future rewards, you don't have those yet. You haven't taken those future actions yet. So the only thing you can do is you can plug in your v hat pi. Step 3, you can evaluate the advantage. You can evaluate the advantage at state S and action A because you already have all the things you need for that. You have S prime because you just executed this transition. You have your v hat pi because you just fitted it here. So you can evaluate your advantage even though you haven't yet executed the rest of the trajectory. So your advantage is there. And then you estimate your policy gradient. So you take grad log pi for the action that you just took, multiplied by the advantage that you just calculated, and that's your gradient. And then you add your gradient to your parameters, and that'll get you a better policy. And in principle, you can do this every single step. I'll tell you right now that the algorithm as written on this slide is typically not going to work for neural network function approximators, and we'll talk about the practical reasons for that in a second, but theoretically, this is a fully online algorithm that you can use to update your policy every single step. And then, of course, you repeat. Question?
Do we have to use a discounted version for the online algorithm?
So the question was, do you have to use a discounted version for the online algorithm? The answer to whether or not you have to use a discount is actually pretty complicated because it depends a lot on the structure of your rewards. The only time where you really have to use a discount factor is if your total rewards might go to infinity. That is not always the case. Even for infinite horizon problems, you might have problems where your rewards actually do converge to some total even for infinitely long sequences. But of course, it's a lot easier to guarantee that they'll converge to a finite total if you put in a discount. So there are some special MDPs that you can come up with where just because of how the MDP is structured, you're not going to get infinite rewards. But usually everyone just uses a discount factor because then you don't have to figure out whether your MDP satisfies these assumptions or not. Okay, so I'm running a little short on time, so I think I'll actually skip the break and go on to the next part, so sorry about that. But we only have about 20 minutes left, so we'll be done soon. What I want to talk about next is some practical details about these actor-critic algorithms. So I told you that the online actor-critic algorithm, as I described it, wouldn't really work in a deep RL setting. The main reason for it is because it's doing these updates with a single sample. So it's using a single sample to update the value function, using a single sample to update the policy. And in practice, if we're training deep neural networks, doing stochastic gradient descent with a single sample is a very hard way to optimize a neural net. You really want something that looks more like a batch. But before we get into that, a few details about architecture design. If you were to design neural network architectures for actor-critic algorithms, there are a couple of choices that you can make. And actually, there are very reasonable options that you have available. One very reasonable option is to use two completely separate neural networks, one for the value function and one for the policy. This is a very simple way to go. It tends to be pretty stable, meaning that it's relatively easier to get these kinds of architectures to actually work. The main downside is that there are no sharing of features between the actor and the critic, which means that if, for example, your states are images, then you have to separately learn good image features inside the critic and inside the actor. And maybe you might think that, well, good image features should be shared between the actor and the critic, and you can go that route too. You can actually have a single neural network with two different outputs. So maybe you have two separate heads at the top, one for the value function, one for the policy. This gets you the feature sharing, But in practice, it can be a little harder to tune hyperparameters for these kinds of designs because you have two very dissimilar gradients flowing into this model. You have the gradient of the squared error of the value flowing from this head, and you have the policy gradient flowing from this head. The policy gradient also has, somewhat high variance. This gradient might have some really wacky magnitudes because of the squared error. So in practice, that can cause a little bit of trouble as far as stability, and you have to be a little bit careful about putting weights on one or the other in order for them to balance out properly. So this kind of design can in principle be more efficient because of the sharing of the features, but can take a little more hyperparameter tuning to get right. All right, online actor-critic algorithms in practice. So that batch thing that I mentioned, you can actually fix it. So this update, where you update the value function to match the targets, it works better if you have a batch. But of course, it's online, so if you want a batch, what you have to do is you have to have multiple parallel workers. You have to have multiple learners that are taking multiple actions up here in parallel and then giving you multiple target values. And the same thing for the policy gradient. For the policy gradient, it also really helps to have a batch so that you average that gradient over some number of samples. One good design for on-policy actor-critic algorithms like this, if you want them to be online, is to use a parallel setup. A very simple parallel setup with synchronous workers is to have a few different threads that are all collecting transitions. So these different threads might literally be just running the simulator. They don't actually have to be threads. You can do it sequential too if you want, but obviously more efficient to parallelize. So they run the simulator, collect a transition. Then for each of those transitions, you can estimate your targets and so on. And then you have to synchronize, because if you're going to be changing your v hat pi, the v hat pi is used by all the threads, so you have to put a synchronization point. And then the same thing for theta, you have to put a synchronization point. And then you can collect more experience in parallel, compute more target values, then synchronize again, and so on. You can also have an asynchronous version of this that's very similar in spirit to asynchronous SGD. So the asynchronous version has some central parameter server. All the workers are running without locks, and then every time a worker gets a transition, they might go and update the parameters, send a gradient back to the parameter server, and once you've accumulated a gradient from enough samples, then you apply that gradient, and you get a new policy. So here, the workers might be a little bit out of sync, so this guy might be executing a policy that is old because it's already changed since this guy might have updated it, but in practice, this kind of thing can actually work pretty well. So we'll have a much more in-depth discussion of asynchrony and parallelism and reinforcement learning towards the end of the course. But here I just wanted to give a quick preview simply because for online, on-policy actor-critic algorithms, oftentimes parallelism can be important to get them stabilized because it lets you use a batch size of larger than 1 up here. Okay. So now what I'm going to talk about for kind of the last technical portion is a discussion of actor-critic algorithms that are a little bit different. So far, I talked about using the critic as a better estimate of the advantage. You can actually also use the critic to get a better baseline. So why might we want to do one or the other? The actor-critic algorithm, as I described it so far, gives you a policy gradient with much lower variance, because the critic is estimating that big expectation instead of using just a single sample sum. The problem with this actor-critic gradient estimator is that it's not unbiased anymore, because your critic is not going to be, in general, perfectly correct. So if your critic is wrong, and any function approximator is going to be wrong, if your critic is wrong, then in expectation, this thing is no longer actually equal to the policy gradient. We might still prefer that because of this thing. So you might still prefer a biased but lower variance estimator over an unbiased but higher variance estimator. But the fact that it's not unbiased can cause trouble. The estimator that we had before when we talked about policy gradient on Wednesday was unbiased, but of course has higher variance because it's a single sample estimator up here. So can we use a critic and still have an unbiased policy gradient? It turns out that we can. So we can use v hat pi and still keep the estimator unbiased. And one of the ways to do that is to use it as a baseline. So you'll all prove in homework 2 that using a state-dependent baseline is just as unbiased as using a constant baseline, and this is actually fine. And the reason this might help is that if v hat pi is a good estimate of the value, then in expectation, this thing will actually come out to be the advantage, and if the reward, basically, if the bulk of these rewards are a constant action-independent term, like the value of the board state, then a lot of that will be subtracted out from subtracting out the value function. So in practice, using a value function here will give you much smaller numbers, and that might give you lower variance because the numbers are smaller. So here you have no bias, because state-dependent baselines are unbiased, even if, basically for any function. So the closer this thing is to the true value function, the lower the variance will be, but it's always unbiased. And you'll have lower variance, not quite as low as up here, because you still have this sum of rewards, but lower than if you used the constant baseline. There's a question, yes?
Last week we proved that there's a best baseline for lowest variance. How is that?
Yeah. So the question was, last week we proved that there is a particular baseline that minimizes the variance. How does that relate to this? So the detail is that last week we proved that for a constant baseline, a baseline that does not depend on state, the optimal solution is that reward weighted by gradient magnitude. If you allow the baseline to depend on state, then the optimal baseline is actually different. It's still not equal to this. It still has that weighting by the gradient thingy. So this is still not the optimal state-dependent baseline. But just in the same way that average reward was a good and simple alternative to that funny gradient-weighted thing, this is a good alternative to the truly optimal thing. And in practice, it's simple because it's just a scalar value, whereas the optimal one has to be per dimension. OK. So this is actually the thing that you'll implement in homework too. You'll have this value function that you'll implement, and you'll use it as a state-dependent baseline. Now, at this point, some of you might be thinking, OK, well, baselines that depend on state are good. What about baselines that depend on action? Surely those must be even better. And the answer is that you can actually have baselines that depend on action. Those, however, are no longer unbiased. So if you were to integrate out this thing, you would get 0 in expectation. But if you made it depend on action, you would not get 0 anymore. But if you're careful, you can still use them. So state and action-dependent baselines, they're also sometimes referred to as control variates in reinforcement learning. It's the same kind of control variate as in statistics. They're going to work like this. So here are some definitions just so that we can see them for your reference. You have Q functions, value functions, and advantage functions. And if you have state and action-dependent baselines, they're basically going to look like Q functions instead of value functions. So the advantage that we use when we have state-dependent baselines is the sum of total rewards minus V. This has no bias, but it has slightly higher variance than using the critic. If you do sum of discounted rewards minus Q, that's not actually an advantage estimate anymore. That's actually going to be incorrect. So it's actually going to go to 0 in expectation if the critic is correct, right? Because in expectation, this thing should be equal to this, so it'll actually go all the way to 0. It's not really an advantage. But numbers that go to 0 have pretty small variance, right? So you kind of want those numbers to be small. The issue is that you just have to have a correction term. So you have to correct for the bias that's introduced by this. And how do you correct for it? Well, you can do it like this. So you can write out your policy gradient estimator with whatever you're using for Q hat, maybe the sum of rewards, minus your Q function estimate. And this thing will become very small if Q pi is accurate. In fact, in expectation, this will just go to 0. But it's no longer the correct policy gradient, so you have to add back in the bit that you're missing. So the bit that you're missing is the expectation under the policy of this Q. Now, at this point, you might say, well, we just did something silly. We subtracted a number, and then we added it back in. Right? So how can this possibly help? Well, the reason that this might help is that if you choose Q, remember that Q is a function approximator. So if you choose Q such that the expectation of Q under pi has a convenient closed-form solution, then this second term might be a lot easier to evaluate than the first term. So you can choose Q, for example, you can choose it to be quadratic in the action. If Q is quadratic in the action and your policy is Gaussian, the expectation of a quadratic under a Gaussian has a closed-form solution. You don't need to sample to evaluate. You can actually evaluate the whole integral, the whole expectation. So this part requires samples, but if you choose the form of Q carefully, this part might have a closed-form solution. So then this might actually give you a better estimator. because this part will go to 0 if Q is accurate, and this part will correct for the bias. So if you hear about action-dependent baselines or control variates in reinforcement learning, it's referring to this type of estimator where you subtract off something that depends on the action and then add back in the remaining term to correct for the bias. Question?
If your simulator can reset from any state, couldn't you also just sample that expectation?
Yeah, so if your simulator can reset to the same state multiple times, you could also sample this expectation. That's right, yeah. And there are actually quite a few methods in the literature that have proposed different forms for this Q and different ways to estimate this expectation in a way so as to get a better policy gradient estimator. So if you want to read like one example of a paper that did something like this, you can check out this paper called Q-prop by Shixian Gu. So in general, you can use this critic without the bias, provided that you can evaluate the second term. Okay. So now let me talk a little bit about how you can use these state-dependent baselines and Monte Carlo returns together in different ways. So far, we talked about the standard kind of actor-critic advantage estimate, where you take the reward plus the next value minus the current value. This has lower variance, higher bias if the value is wrong, so we already saw that. Then we talked before about this Monte Carlo estimator where you sum together the rewards, and now we learned that if you subtract off the value function, that also gives you an unbiased estimator with slightly lower variance, not as low as this one, but it's unbiased. So this has no bias, higher variance than the critic one, but lower variance than the pure Monte Carlo one from Wednesday. So we have these two choices. It seems like the choice between them is really a bias-variance trade-off. So AC has lower variance, AMC has lower bias. So then we might say, well, do we have to really pick one or the other? Can we somehow interpolate between them? So can we combine these two and control the bias-variance trade-off explicitly with some kind of scaling parameter? So here's how we can think about getting more fine-grained control of bias-variance trade-offs. As you kind of move further into the future, you would like your dependence on the reward, on the Monte Carlo rewards, to decrease, because rewards further in the future are more uncertain. The discount factor already does this to some degree. So the discount factor reduces variance because it just makes these discounted rewards smaller further into the future. Rewards further into the future are more uncertain. So if these are all the different possibilities, then over here you have really big variance between the different rewards. Like if you ask me like, oh, what are you going to do 20 years from now? I'll say, well, okay, maybe I'll be like an astronaut or a bus driver or something. Like there are so many possibilities. Who knows? Maybe my reward will be really high. Maybe it'll be really low. Further into the future, there's very high variance. But in the very near term, there's much lower variance. So if you ask me what am I going to do, let's say 15 minutes from now, I'll say, well, maybe I'm going to go get lunch. And that'll give me slightly higher reward because that'll make me happy. So I have smaller variance here because I'm pretty sure that I'll actually succeed at getting lunch. I'm not sure that I'll succeed at becoming an astronaut. So what you can do is you can say, well, your rewards that you get from rolling out these trajectories, they have pretty small variance in the near term, but very high variance in the future. So what you can do is you can basically trust them more closer to your current time and not trust them in the future. So cut them off before their variance gets too big. So basically zero out the rewards after a certain time, put a little break in that thing, and then you'll remove a lot of the variance. And it's so far in the future that removing it really isn't hurting you at all, because by that point those estimates are so bad that they're not really contributing much to your gradient estimate anyway. So what you can do is you can say, well, instead of summing together the rewards from the current time step until infinity, let's sum them up from the current time step until n steps in the future, right? Sum them from now until n steps in the future, and it's an advantage, so you have to subtract off the current value. But now, of course, you have bias. You have error because you've removed these rewards. You wouldn't have recovered that value anyway because there's so high variance, but you are introducing some error. So what you can do is you can add back in an estimator that is explicitly trying to estimate that residual. You can add back in the value function after n steps, right? So you can say, well, I'm going to sum the rewards for n steps, and then after n steps, I'll just put in my value function. And I'll just choose n so that n is small enough that I cover just this region, but not this ugly high variance region. And in practice, choosing n greater than 1 often works better. So if you set n to be equal to 1, you get exactly the actor critic estimator, the AC here. If you set n equal to infinity, you get AMC. But if you choose it to be some number between 1 and infinity, then you can actually trade off bias and variance. So larger values of n will have lower bias but higher variance. Smaller values of n will have higher bias but lower variance. And you can tune that quantity to get you the best signal-to-noise ratio that you can get. In practice, of course, you tune it empirically. There is one particular way to use these multi-step, n-step return estimators that tends to be fairly simple and can work very well, and that's called the generalized advantage estimator. The idea behind the generalized advantage estimator is that you're not actually going to choose a value of n, you're actually going to mix together many estimators for different values of n. So instead of choosing just one n, you're actually going to construct many estimators that all cut in different places, and you'll average them together with some weights. So I can write down an equation for a subscript n. This is an n-step estimator. It sums together rewards for n steps, then puts in the value function multiplied by gamma to the n. And then I can write the generalized advantage estimator as a sum over all possible n-step estimators weighted by some weights wn. And then just by choosing the weights wn, I can express whatever preference I have for the bias-variance trade-off. And a very simple choice for these weights that leads to actually a pretty elegant mathematical expression that can be computed efficiently is to choose the weights so that they follow an exponential schedule. So you should prefer cutting earlier rather than later because you want the rewards earlier on, and you want the value functions later on. So you'd like wn to be larger for smaller n. So what you can do is you can choose them to be proportional to this to some constant lambda between 0 and 1 raised to the power n minus 1. So this will give you exponential decay. So it'll say, okay, the n1 that's going to get the biggest weight, n2 will get a lower weight, and so on and so on. It'll decay exponentially to cut off the variance. This is a little bit of an arbitrary choice, but it ends up leading to a very simple form once you actually work out the math for it. So this, if you actually sum together all these estimators, this is not the simple form. This is just to make it explicit what's going on. If you actually plug that in, plug in these weights in here, and plug in the equation for a subscript n in here, what you get is you get the current reward plus gamma times 1 minus lambda of the value function. So 1 minus lambda is the weight on cutting off the trace here, plus lambda times the next reward, etc. 1 minus lambda times the next value, plus lambda times the next reward, and so on and so on and so on. So each of the reward terms has a multiplier in front of it, which is gamma to the t times lambda to the t. Right? So lambda is directly cutting off those distant rewards, and all the value functions have a gamma to the t, lambda to the t minus 1 times 1 minus lambda. And there's a neat kind of telescoping something that goes on here that I'm not going to go through the algebra for it, but it turns out that if you actually collect all the terms, you can simplify the expression for the GAE estimator to just be gamma times lambda raised to the power of t prime minus t times these delta things. And the deltas are just your estimates of the advantage. So what you're actually doing is you're averaging together a bunch of advantages. And there's a neat little telescoping sums cancellation that makes this equality true. So that's actually very simple. You just compute the advantages at all your time steps and then average them together, weighted by this exponential decay. And the interesting thing here is that lambda it just gets multiplied by gamma. So your discount and this lambda constant, they're kind of serving a very similar role. Gamma is still by itself inside the delta, but on the outside, it's just multiplying lambda. So this kind of just emphasizes that gamma also serves a variance reduction role in these advantage estimators. So it has, the lambda here has a similar effect to the discount once you work through all the math. So just like when I discussed the discounted policy gradient estimator, I talked about how the discount serves a role similar to variance reduction. Over here, there's gamma, which serves a role similar to variance reduction, and there's lambda, which explicitly trades off bias and variance by controlling whether you prefer smaller values of n versus larger values of n. All right, so to review what we covered, we talked about actor-critic algorithms. The actor is the policy, the critic is the value function. The actor-critic algorithm reduces the variance of the policy gradient. Policy evaluation refers to fitting the value function to a given policy without modifying that policy. So it's fitting the value function to a policy. Discount factors They allow you to handle infinite horizon things. They simulate your fear of death, but you can also interpret them as a particular way of reducing variance. Designs of actor-critic algorithms. You can have either one network with two heads or two networks. One network with two heads has some feature sharing. Two networks might be easier to train in practice. You can have batch mode or online actor-critic algorithms. If you're using deep neural networks, then the online algorithms, maybe you should think about parallelizing them so that you have batches of size greater than 1. I talked about state-dependent baselines, which are another way to use the critic while remaining unbiased. And you can combine the biased actor-critic estimator with the unbiased Monte Carlo estimator to get n-step returns or generalized advantage estimation. A few videos, a few examples of actor-critic algorithms in action. So this video, which I've shown a few times before, this is actually from the paper that introduced the generalized advantage estimator. So it's a batch mode actor-critic algorithm that mixes Monte Carlo and critic-based estimators on this exponential scale. And that gets this humanoid guy to run around. In the paper, you can also see other finding creatures running around. So it's a blend of Monte Carlo and function approximator estimators. Here's another example. This is from a paper called Asynchronous Methods for Deep Reinforcement Learning, which introduced an algorithm called A3C. That's an online actor-critic algorithm that uses multiple parallel workers to construct a batch. It actually also uses an n-step return estimator for a small value of n, around 4. So it's an online actor-critic parallelized batch algorithm. And here in this video, they have their network. It's actually a recurrent neural network that's learned to navigate this maze to locate some kind of object. That's a funny pear-shaped thing that apparently gives it a lot of reward. All right, some suggested readings if you want to learn more about actor-critic algorithms. Some classic papers. Basically, there's only one here that I would really recommend you check out if you want to get kind of the foundational work on this. This is the paper by Richard Sutton that introduces the policy gradient theorem. This also talks about that causality sort of time decomposed estimator and the actor-critic version of it. Deep reinforcement learning actor-critic papers. This is the A3C paper, the one for which I showed that maze navigation video. This is the generalized advantage estimator paper. And then this is the paper with the action-dependent baseline QProp. So if you want a few examples of recent papers, you can check those out. Okay, next week we're going to start talking about Q-learning algorithms and methods that do not try to explicitly learn a value function, or a policy, but only a value function. So I'll see you all next week.
Hello, Professor.